Well, first of all, I forgot to send an announcement to the class yesterday, but I'm going to make it now, and I'll follow it from next week. Okay, so the class attendance is reducing every week. I know it's kind of normal in all the courses, but probably this is not acceptable. So, given the fact that people have an option to join via Zoom, a hybrid option which is not available in a lot of courses, it's totally not acceptable for someone to completely skip a lecture. The only reason why you could skip a lecture is because you have a clashing course. Very few of you have that. I gave permission to take the course with that, or you are sick, that you really cannot take the course, right? So for the rest of the semester, I know it's not too long. Probably initially I thought probably I should not release the lectures and just keep it live, but that is going to affect students, sincere students who wants to go back and watch the lectures. So for the rest of the semester, probably I'll randomly pick a day and take attendance and just give bonus points for people who are sincere enough to come to class every week. Okay, so let's see if that motivates people to come to class. I hate to do this, but I think the other one is a negative reinforcement, so let's just do positive reinforcement. Okay, so before we get started, so your assignment 2 grading should be released anytime soon, and A3 was out last week. So, well, based on the feedback about the time it takes for the assignments, so TS experimented with giving you the starter code for A3. So I'm curious to know your feedback. So if you guys like it, probably we will consider redesigning assignments next year, so with some starter code. So please go and fill the anonymous feedback form and give more feedback on how easy or hard the third assignment is. And of course, if you have you skipped PyTorch tutorial and you don't know what is PyTorch, this is going to be a difficult assignment for you. So if you have missed the PyTorch tutorial, probably you should go back and watch it before you start the assignment. Okay, so other than that, so the feedback for your project proposals should also be available in a day or two. So my plan is to go through all the proposals and give very high level feedback to help you, mainly to put a flag if there's something totally wrong or something that you should do in a different way and so on, right? So but majority of the evaluation is going to happen towards the end. Okay, and there are also some questions about the end term, the final exam, in Piazza, I guess. Okay, I think I said this before, I'm repeating it. So the exam dates are not set by me. Okay, so can somebody tell me when is the exam? Is it some 15 or 17? 13. And is it morning or afternoon? Okay, I think it's something like 1:30 p.m. I guess. So I'll verify and post it in the lab, in the course website. So whatever the time given by the university, that is what we are going to follow. Okay, so if we have a different time, then that is going to clash with other exams, which we don't want to happen. So if you have one exam in the afternoon, one in the morning, it is unfortunate, but that is not in my hands. Okay, so you took these two courses on university schedule. So probably these kind of things you should talk to the admin, but I don't think they can do anything now. I assume this is a common business every semester. Sometimes there is clashes. So I think one of the students said there is an exam in the afternoon immediately followed by another exam in the morning. So we cannot change that. Okay, so and for our exam, we are going to, if it is 1:30, we will do 3 hours from 1:30. I'll release the exam paper at 1:30. So you will submit back your answers in 3 hours. Okay, so we will be following the exact time. It is just that it is going to be open book take home exam, instead of sitting in the classroom and writing the exam. Okay, so let us get started. So to give you a very quick recap of what we have done so far, right? So 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 far we have seen various ways to solve the oral problem, right? So we started with dynamic programming, which was like computationally intensive, and also it requires the access to the dynamics function of the world. And then like we talked about Monte Carlo, TD, right? So n-step TD, which is a combination of TD and Monte Carlo, right? So, and these were all in some sense like what we called last week as value-based methods. Right? So in last lecture, like we discussed about policy gradient methods, right? Like so which is based on this idea that like why should we first learn a value function and then use the value function to learn a policy, like or compute the policy? Like so why can't we directly approximate the policy itself, right? Like so like which is more useful when you're especially in function approximation setting, because the moment you start doing function approximation with value function based methods, like you lose the policy improvement theorem, right? Like so like it doesn't hold anymore. So whatever we are doing is just empirical. Like so like it works, sometimes it doesn't work, right? Like on the other hand, what is nice about policy gradient methods is like even with function approximation, like where you're trying to approximate the policy by using a linear function approximation or neural network, it doesn't matter, right? Like so policy gradient theorem gives us some hope that like whatever variance that you're computing would actually take you in the right direction towards maximizing your performance, right? Like so which is a very nice like promise. Like so, and based on that assumption, like we developed a bunch of methods for like which are policy based, like so like we started with reinforce, and of course reinforce with baseline. Let's call them the same algorithm. And then we talked about acrocritic, which is not just policy gradient method. Like so like let's just say this is a combination of policy and value, right? Because you have your actor, which is a policy network, and your critic, which is a value network, and like they are both learned together. And in some sense, it's a hybrid of policy-based methods and value-based methods. Is it clear? Okay, so this is the landscape of algorithms that we have seen so far, right? Like, so today's lecture is going to be about yet another way of solving reinforcement learning problem. Okay, so here we're going to talk about model-based reinforcement learning. Okay, so far all these algorithms that we have seen in this course, right, except for DP, okay, or in some sense like what we can call as model-free algorithms. Okay, now when I say an algorithm is model-free, it does not have access to either the real environment's model, like it does not have access to the dynamic function, or it does not even try to estimate the dynamic function. There is no model. Like so, like given a state, I'm directly trying to learn an action or action value and then action. Okay, so that is model free. On the other hand, like we did see dynamic programming, like where we had access to the dynamics function, right? Like so, which is in some sense the model of the world, right? Like so when I say model of the world, okay, so it basically means the dynamics function, which given a state, an action, it is going to return as the next state, like or a probability distribution over the next state, and also reward distribution. Like so what is the reward distribution like that I would get like by taking this action in this particular state, right? So this is my dynamic function, like which is probability of st plus 1 rt plus 1 given st, right? Now the real, like the actual environment that like we are interacting with, it already has this internal dynamics function. And in the case of dynamic programming, it had this very strong assumption that you have access to the dynamic function. So suppose somebody gives you the dynamics function, then all that dynamic programming is doing is some sort of planning to discover the optimal policy. Okay, so there is no learning happening in DP, right? These are learning-based methods, MC or TD or ends to TD, but DP is not a learning-based method. You don't even need to interact with the world to do DP, right? So you have the distribution, you will do some estimations with the distribution, okay? So which is what we're going to call as planning, okay? And the planning algorithm is going, like in DP's case, or value iteration or policy iteration, is going to give you an optimal policy or near optimal policy, right? So that was the idea behind DP. So now with this introduction, right, of model-based R, so now we can classify all the algorithms that we have seen or we will see in reinforcement learning as either model-based or model-free. Okay, now model-based, so far the only example that we have seen is DP, right? And for model-free, we have seen Monte Carlo DP. Okay, now the main difference between model-based and model-free methods is this. So in the case of model-based methods, the focus is on planning. Okay, and in the case of model-free methods, the focus is on learning. Well, of course, one can combine both learning and planning. So we will see some of those examples today. Okay, but probably other way to put it is so what is missing in model-free methods is this notion of planning ahead, or planning based on the previous experience and so on, right? So which can be easily done if you have a model-based algorithm. Okay, is that clear? Any questions? So there are some questions about exam in the chat. I will take it a little bit later. Any questions so far about what is model-based algorithm? Okay. Now, as I mentioned, whenever I say the word model, okay, so it just means the probability of ST plus 1, RT plus 1, given ST and RT. Right? Now, most of the real world applications that we are interested in, could be stochastic. If it is deterministic, then probably you don't even need this probability distribution, right? So if there is only one possible next state and only one possible next reward, so it is easy to model, right? So however, for most of the interesting applications, you are going to have stochastic environments, in which case the model also has to be stochastic, right? The model should have an estimate of what is the probability distribution of the next states and so on, right? So in general, we will talk about stochastic models. Okay, now there are two types of stochastic models. Okay, so we're going to first name them and then I'll explain what they are. So the first one is distribution model, and the second one is sampling model. Okay. So what is a distribution model? A distribution model is going to give you a description of all possible next states rewards and their probabilities. Or in other words, this gives you a complete distribution of ST plus 1, RT plus 1. Okay, for example, let's say I want to assume that the states are distributed in a Gaussian manner. Okay, so now I could just have probability of ST plus 1 given ST AT, modeled using, let's say, a function approximator for Gaussian output, right? So similar to the continuous action space example that we have seen in the last week, right? So you could model theta, you could model mu and sigma of the Gaussian, which represents the next state distribution, using a linear function approximator or using a neural network, right? So now that is my stochastic distribution model for the next state. Similarly, I could have a distribution model for the next reward as well. Like if the reward is continuous, then I could have a Gaussian again and model my reward using the Gaussian distribution, right? Like so, but that is distribution model. Like however, like sometimes like you will also see sample models, okay, where the idea is like it is going to produce just one of the possibilities. Okay. However, this is sampled according to the underlying probability distribution. So in this case, my model will not give me all possible next states and all possible next reward. Okay. Instead, the model is going to give me a sample from this distribution. Okay. Now, is it distribution models more powerful? Like, so it gives you access to a complete state of the environment, right? Like, so then why would someone prefer sample models? Yeah, so computationally, distribution models are very expensive. Okay. Also, let's say we want to learn these models. Okay. So learning a distribution model is also going to be like difficult because you have to model the distribution itself, right? Like so. On the other hand, like sometimes it is easy to sample from a distribution than computing all possible probabilities. Okay. Let me give you an example. Like so, I think the example that the book has is modeling the sum of a dozen dice. Okay, so I have 12 dices, like I'm throwing the dices and like I compute the sum. Now this is a random variable, right? So now it is easy to sample one of these events, like which is basically rolling the dice 12 times and like adding the value, then actually enumerating all possible like combinations and what are their probabilities, right? So similarly, like for a lot of interesting problems, we have really good simulators available, like which can give you what is the next state. But if you ask the simulator what is the probability for this particular state, it is going to be a hard problem. Okay, so like especially for robotics tasks, like so we have simulators like Ujoko where like given a state of the robot, like let's say there's a robotic arm, like given the state of the arm, like now this simulator is going to do some physics-based simulations and tell you, okay, so if you take this action, this is how this is going to move. Okay, now that is easier to compute, but when I say easier, it is not such trivial thing. Like it is easier to compute than having a distribution model over all possible states here. Is that clear? So now, if we go back to DP, right? So like what kind of model was DP using? Is it distribution model or sample model? Distributional model, right? So DP took an expectation over all possible next states. So DP was using distribution model. Okay. On the other hand, we are going to see some sample-based models today, which should be easier. Okay. Now, given any state and action, okay, these two types of models that we have seen are going to have like different characteristics or like different things that they could perform. Like so, for example, in the case of sample models, so given a state and action, it is going to give you the next state and reward. So sample models can produce transitions. Okay, so it just tries to predict what is the next state, what is the next reward. Distribution models can actually generate all possible transitions. Not just all possible transitions, but also their probability of occurring. Yeah.
So the sample-based models will give me like the next state can reward.
Yeah.
So how Monte Carlo is not sample-based. We only need like the next state and things like that.
Yes, Monte Carlo is. Oh, Monte Carlo is sample-based. Like, but okay, we will talk about combining these learning methods with planning methods. Like, so Monte Carlo is sample-based for sure, right? Like, so, but the only difference is in the case of Monte Carlo, you don't have the notion of model at all. Like, so, like you are directly interacting with the world, right? Because other.
This is like a simulation of something.
Oh, okay. So if you're using a simulator, like which is an approximation to the real world, so then probably like you are doing some sort of model-based stuff, okay. But most often when we do Mijoku, like we don't treat that as a simulator because we are not going to train with the simulator and then test with a real robot, okay. So like learning policies in simulator and then transferring it to real world like is a challenging problem by itself. Like so we will not probably, I don't know like what we're going to talk in the last 2 weeks, like advanced stuff, like but probably we will not touch that for this edition of the course. But when one easy way to differentiate like algorithms is whether the algorithm is learning a model of the world or not. Okay, so we are going to like DP is like, I call DP as model-based method, like, but there's no learning involved. So, like, if you want both learning and planning together, right? Like, so then Monte Carlo doesn't have the planning component. Like, so, like, it doesn't have, it doesn't learn a model of the world internally, so that it can use that to do better, to come up with better policies. Things like Monte Carlo DD, like they are model free in the sense they don't know like whether it is simulator or real world, like, and also they don't learn like or estimate the dynamics function. Okay, so there are some questions in the chat. Isn't the probability P of s plus what plus one? Yeah, okay. Somebody answered it. Okay. Okay, now this is given any state in action, right? Like so now similarly, I can just like give the start state. Let's say I give the start state and the policy. Okay. Now a sample-based model can actually generate one complete episode. Okay, so I give you the start state. I also give you a policy. Now, given the start state, you will ask the policy for an action, right? Like, so given S0, you ask the policy for an action that is going to give you some A0. Okay. Now, you have the one-step sample model. So the sample model is going to tell you, okay, this is the next state. This is the next reward. This is the next state. Okay. So this part was from the policy and this part was from the model, sample model, right? Now, given this state, I can ask the policy what should be my action. So I'll get A1 and so on, right? I can generate a complete episode by using sample model, okay? However, distribution models are much more powerful. Like the distribution models can actually generate all possible episodes, okay, and also their likelihood. Like, so how likely is that I'm going to generate this episode? How likely is that I'm going to generate this episode, right? Like, so in general, distribution models can give you everything that you want, okay? It's kind of like the generative models in classification, right? Like, so like where you, once you model the distribution of the data, like, so then you can answer any question that you want, right? Like, so however, like sample-based methods like are like simpler and easy to use, okay? Any questions about distribution and sample-based models?
Model-based method without interacting with the world, we try to
Okay, so if you have the model, then without interacting with the world, you can just learn a policy.
After the model, not before.
Yes, which is what DP is doing, right? However, well, we are going to see all flavors of model-based learning today. Okay, so like, how do you learn the model, right? Like, so like now you can actually learn the model simultaneously with your policy, so that as the model improves, like model is helping more for the policy to improve, and as the policy improves, like you're discovering better regions of the world and like you are improving the model. Okay, so you can either learn the model first and without interaction estimate a policy, or do it simultaneously, or you could just do it in phases, like so do some model learning, then do policy learning, so then do model learning, then do policy learning. So we can combine these things in whatever way we want. Okay, so far I only talked about like what is a model, right? Like it's the next state, next reward estimator, or like it could be distribution based or it could be sample based. I think so. Now, how do we use this model? So well, we should also talk about how to learn the model. Let's come to that a little bit later. Like, but for now, like, how do we use this model? Okay, so we are going to use this model mostly to simulate the environment. Okay, and our goal for modeling is simple. Okay, so any method that we are trying in this course, like the goal is always same. Like, so what is our goal? What?
Like the dynamics function.
No, our goal is not to learn the dynamics functions. What is our ultimate goal? Yes, so there are also answers in the chat. So yeah, so that's right. Like, so our goal always is to learn the optimal policy, right? Like, so like our problem is all about like how do I find this optimal policy which is going to give me maximum reward. So even when we are modeling the world, okay, our goal is not to have a better model of the world. Okay, now this is kind of similar in spirit to the value-based learning arguments, right? Like, so like if you think about it, in value-based learning, our goal was not to learn the best estimate of the value, right? Like, so that is what we discussed in the function approximation for value-based methods. Like, so like I mentioned that it is not very clear if the VE error that we saw for value-based methods is actually the optimal error that we should be minimizing for, because our goal is not to minimize the error in value prediction. Our goal was to come up with a better, like, or optimal policy, and value estimates were just a mean towards that, right? So similarly, like whenever you have a model, okay, so the goal is always the policy. Okay. Now the way in which models are going to find better policy is by using planning. Okay, so now how many of you, well, most majority of the classes in this week, so I don't know how to count, but how many of you have taken an AI course, like the classical AI course, and seen some planning? Okay, hopefully most of you. Okay, so it's okay if you have not, like, but you would appreciate this more, like if you have done some planning before. So in traditional artificial intelligence planning methods, right? Like, so there are two types of planning. So one is called state space planning, and the other one is called plan space planning. Okay. So the idea of state space planning is you have a goal, and you start from some start state. Okay. Now you're going to search for a plan in the state space, like from this state. Okay, which next state should I go to? From there, which next state should I go to? From there, which next state should I go to? Right. Like, so, or in other words, like you traverse through the state space, right? Like, and find the path which is most promising in terms of returns, and take the action which is going to take you towards that. Okay, so that is the idea of state space planning. Like, to give you some illustration, like, so let's say this is my current state. Okay, and I have, let's say, 3 possible actions to take. Now, which action to pick? So state space planners would basically try to go through the whole thing. Okay, it will go through the next stage, next stage, next stage. Maybe it reaches the end of the episode, or maybe it stops at some point, like with some approximations, and looks at and backs up the value and try to come up with an estimate for value for all the 3 actions and pick the action which has the maximum value. Okay, now there is no learning happening here. This is just planning. Okay, so we haven't started discussing about combining learning with planning. So in this case, I am in a state, I want to plan what is my next action. Now, of course, like if you're using value functions for this, like you have to learn those value functions. That's a separate thing. But for now, like given some way to estimate the value functions, then you can just look ahead for like many steps and pick the most promising direction. Okay, so that is state space planning. Now, in reinforcement learning, like we mostly use state space planning. Okay, so however, there is also plan space planning in AI, like so, which we will not talk much about, but nevertheless, it's worth knowing. So the idea of plan space planning is like you will be searching for the optimal plan in the space of plans. So you start with the partial plan and then say, okay, so if I add this part to the plan, like, so what happens? If I add this part to the plan, what happens? Okay, it's kind of very difficult to do plan space planning with like sequential decision making. So we will not use plan space planning. So we'll just use state space planning. Is that clear? Yeah.
Yeah. So when you describe the state space planning, it still seems like Monte Carlo is similar to doing what's for state space planning.
Yes. So true. There's a lot of similarities. We are going to talk about that. So the only difference, well, the difference with the MC methods that we have, well, we are going to see Monte Carlo based planners, okay, but the difference that we have between the MC methods that we have seen in the beginning of the course and this is those MC methods were learning value estimates. And once you have the value estimates, you constructed a policy. Okay. But here we're going to do different things. So we're going to use Monte Carlo methods, but not for learning the value estimates, like, but for planning what action to take. Of course, they are very similar. We're going to see the similarities and differences soon. Any other questions? Okay, there is actually a question. Okay, there are a couple of questions. So can you define what a plan is? Okay. Probably I don't want to get into the classical definitions like so. So when I say a plan, like it is in our case, it is basically like what action to take. Okay, so our policy is the plan. Now there's also another question which is similar to your question, like what's the difference between state space planning and Monte Carlo and step 3D? So there is not a lot of difference. Like so, we're going to see like how they all can be put together. Okay, so now here is okay. Now I think we talked about what is a model, which is basically this distribution over the next states, right? And we also talked about like how to use it, which is basically through this notion of planning, right? Now, probably I'll quickly talk about learning the model. Okay, so but we are going to combine all these things together. So we will repeat this again and again. Okay. Like what kind of models we can learn in practice? Like so, for example, like you could have a tabular model. Okay, so when I say a tabular model, like it kind of tries to maintain this table of what is the next possible next state and next possible reward. As you can imagine, it could work for simple grid worlds, but definitely not for even medium-sized problems, right? Like which means you need function approximations, right? Like so, like you could use linear model. in which case, like, you given the state, an action, you have a linear function approximator, which tries to predict the next state. Is that clear? Or you could have complex neural networks, which takes a state, an action as input. Okay, and you have this neural network which tries to predict the next state. And is that clear? Now, I think there was this one anonymous feedback a few weeks back about why I am switching between chapters in the book. So one of the reasons why I wanted to delay model-based RL, like uncover function approximation, is now we can also talk about function approximations in this lecture. Like, however, the book just talks about tabular methods for model-based RL. Okay, so like this is just more convenient, and like we could talk more about models with function approximation, which we could not have done if we covered this in like 5th week of the course. Okay, so now I'm not going to talk about learning the model in more in detail. Like, so like this is simple function approximation problem. Like, so you collect a bunch of states and actions and bunch of next states and rewards. Then you do batch updates, like with probably a squared error or a negative log likelihood if it is a Gaussian distribution and so on, right? Like, so like this is similar to function approximation. Okay, so we will not talk about it in detail because it is not very clear whether we are going to do this as a separate phase. We are going to mix things together. So let's move to that. Okay, so now, so what are the ways in which I can combine this idea of planning and learning? So this is where all your confusions about relationship between TD, Monte Carlo, and all these things will be more clear now. Okay. Now, there are at least 2 ways in which the model of the world could be useful. Okay. So we'll start with the first way and then discuss the second way. The first way in which model could be used is that you use the model to learn better value functions and policy, and by default, like policy, right? So you can use the model to improve your value function. Okay, so this is more like about methods which use the model to simulate more transitions, and then use these transitions to do Monte Carlo or TD or whatever you want to do. Okay, and get basically you can see models as another way of getting data. Okay, so let's say interactions with the world is costly. Okay, if you have a simulator of the world, then you could just mix your transitions, right? Like if you think about Monte Carlo or TD or n-step TD methods, there's nowhere in the algorithm which makes an assumption that you're interacting with the real world, right? All these methods are transition based. They will work fine as long as somebody gives you the transition, right? So now it doesn't matter if the next state comes from the world or from a simulator of the world or from a learned model of the world. Okay, so this is the first class of algorithms. Okay, so we're going to talk about that first. Now there's also a second way in which model could be useful. Now let's say I have done model free learning. Okay, like I have a good policy. Okay, now I can use the model to improve the policy. Okay, during decision time. Okay, so here the model is not used to learn the value functions. Okay, so this is more, so this is also known as decision time planning. So this is where the kind of tree search methods, like, so we're going to see Monte Carlo tree search today. Like, so these kind of methods fall under the second umbrella, which is using the model, but not during the policy learning, like, but rather during the decision time. Okay, so like, so you are in a state, you have to take an action, you have a policy. The question is, can I actually improve on this policy that I have, like existing policy that I have, if somebody gives me more computing? Okay, so this is you need more computational time for decision time planning. On the other hand, if you're going through the first approach, you're kind of doing everything in background. Like, so once you have the policy, then it doesn't matter whether the policy came from model-based method or model-free method, like you just act, right? On the other hand, like this is the second approach is a little bit costlier because you have to do this online planning, like before taking an action. Is that clear? Any questions about, well, of course, you could also combine these two together. Okay, so you can use the model for learning the value functions and again use the model for like improving the policy that you have learned. Okay, so one thing that you could notice today is like we are really not talking about specific algorithms like previous lectures. Like, so this is mostly philosophical in the sense you can design 100 algorithms based on combining all these things. Okay, so whether you're learning the model first or you're learning both together, or like you're learning in phases, whether you're using the model for learning, just learning, or whether you're using the model for acting and so on. Okay, so so today, like, we will not have we'll have a couple of algorithms, but mostly we will talk about various ways in which we could be combining planning and learning. So any question? Okay, so well, now let's start with the first approach. Okay, so the first approach is where the model is used while learning, right? So here is the general structure. Like, so you will start with the model, okay, and you will use the model to generate some simulated experience. Okay, now by using the simulated experience, you're going to learn the values by backup. By using these values, you're going to learn the policy. Okay. Now, if you think about this particular way of doing model-based R, then there is not a lot of difference between this and the model-free methods that we have seen so far, right? The learning methods that we have seen so far are not very different from this planning method. Like, so the only difference is this part. Like, instead of having the simulated experience in the model, like if I can actually interact with the model, right? Like, so now maybe I'll write the other thing as well. So now this is model-based RL, right? In the case of model-free RL, like you will have the real world, right? And you will be interacting with the real world. And based on the interaction, you will learn the values and you will learn the policy. Right? So now, most of the R algorithms that we have seen so far, so they actually are in this space. Right? So in some sense, you can seamlessly merge both model-based R and model-free R. Like for example, let's take Q learning. Okay. Now, if you do Q learning, sometimes with the real world interaction, and sometimes with the simulated experience. Okay. I can also do Q learning with just simulated experience if I have a model. Right? So here is such an algorithm. Like, so this is random sample one-step tabular Q learning. Okay. So what do you mean by that? So let's say you are in a state, okay, and you take some action. Okay. Now you take this state in action, you send it to a sample model. This sample model is going to give you the next reward and the next state. Okay. So now you have the transition that you need to make a Q learning update, right? So now I can actually apply the standard Q learning algorithm, like updates for this particular transition. Okay, now this is very similar to Q learning, except for the fact that instead of interacting with the environment, I'm interacting with a sample model. So all the guarantees that we have for Q learning, like how Q learning will converge to the optimal policy for, like in tabular city. Okay, so for how it will converge to the optimal policy for interacting with the environment is going to transfer, but in this case, this algorithm will converge to the optimal policy for the model. So given a model, what is the optimal policy to achieve maximum return within this model? Okay, so we will converge to that under the same guarantee and conditions that we have for Q. Is that clear? Any questions? Okay, so there's a question in chat. Second. Where does the learning model come in place? Oh, okay. So the question is, okay, that's a good question. So the question is, where does the learning model come into place here? So for this particular, well, we still are not talking about learning the model and the policy together. Okay, so in this case, like this model is given. So however, we have learned this model. So like imagine you collected lots and lots of transitions from the world. Now you can learn an accurate prediction model, like which predicts the next day. Okay, so the model is learned already. So like, but we can learn them together, like which is what you will see after the break. Like I don't want to stop now in 2 minutes. There is also another question: will you show equivalent algorithm distribution models? Well, if you have a distribution model, then probably you could do, because I think we are going to talk about it soon. So if you have access to a distribution model, then you should be able to use algorithms which are doing expected updates, right? So things like value iteration, policy iteration. So we should be able to do value iteration with the model. So that would be an example for algorithm, like a similar algorithm with distribution model. Okay. Okay. So probably we will stop here and take a 10-minute break. So then we will talk about DINA, which is a general framework for planning, acting, learning together. Like so, how can we learn the model of the world simultaneously while acting in the environment, while also learning the policy? Okay, so we will talk about that after the break. So we'll continue at 10:30.